So, hi everyone. As Jeremy introduced me, I'm Rohan Yadav. I'm a second-year PhD student at Stanford University, and I'm advised by Alex Eichen and Fred Kielstedt. So today I'm going to be talking about DISTAL, and the topic of the talk is compiling tensor algebra to run on distributed machines. But before I get into that, I wanted to sort of set the stage by talking a bit, why we care about tensor algebra, what are the challenges we face in this domain, kind of why we also need compilers to address the problems in these domains. Okay. So I'm sort of preaching to the choir here a little bit, but tensor computations are ubiquitous in modern computing. We have them coming from various domains, including scientific computing, like chemistry and physics. Tensor computations kind of drive modern machine learning, and they show up in data analysis as well, just to name a few domains. So we clearly care about tensor computations, and they're in a lot of domains. So what do we sort of expect from the systems and languages that we have to program these tensor computations that we want to write? So I think there's three main characteristics. So the first, naturally, is we want correctness all the time. We want to make sure that when we write some of these tensor codes, we're sure they're going to be correct. And so that's not too hard of an ask by itself. We could write naive for loops to run the tensor codes we want, or we could maybe have some libraries that do this for us. Things get a little bit harder when we want to be as productive as possible writing tensor codes. Here I say productivity is maybe the time it takes like a human to write the code. And so getting correctness and productivity, again, isn't too hard. We can write some pretty slow code that does exactly what we want, or we can maybe put together some libraries that implement some components for us. But I think that the key problem really shows up when we want to get good performance. And performance, I mean, here is the time it takes for a computer to actually run the code that we've written. And what I mean by good performance is getting close to peak efficiency out of our machine, whether that's bandwidth or throughput in number of instructions per second. And so as soon as you try to throw in performance into this equation here, things get pretty difficult. And so let's look at kind of why some key challenges of why getting good performance is hard. And then there's three main reasons here. And the first is that the optimizations that we need to apply in order to achieve good performance on modern machines are going to be very low level, very difficult to write, and they're going to sort of be intertwined with the correctness of the actual application that we want. So for example, here I've got a little snippet of a GEMM operation from a BLAS library. And first thing you notice is very low level code. We're using vector intrinsics by hand. This is loop unrolled, and this is just this is a snippet of code within a larger context that is thread parallelized this operation. And so first, the majority of programmers in the world are not going to be able to write code like this, even though they may need it. And if you suppose you know how to write this code and you want to go in and perhaps apply a different optimization, or you want to make the computation do something slightly different, now you're not really sure, are you making sure the code is still correct? If you are, it's very difficult to make these changes. Another problem is that while correctness of software kind of composes naturally, and humans are really good at building and composing software to build more correct software, performance doesn't necessarily compose in the same way. If you have two high performance libraries, the best performing solution is not necessarily going to be to just call them both at the same time or in series with another. And some reasons for this are like, one, you may need to perform a variety of global optimizations across library boundaries, like fusing computation. Or if these two libraries expect sort of different data format inputs, you might spend a lot of your time translating between the two formats. Then finally, there's a large variety of target architectures we may want to target that sort of compound these two problems, such as CPUs, GPUs, TPUs. And libraries for one of these platforms is not going to help you with a library for another platform where you need to get good performance on a separate machine as well. And so having to try and target these multiple architectures is just going to make these earlier two problems worse. And so the research community and industry in the past couple of years have taken an approach of building domain-specific languages and leveraging compiler techniques in order to address these problems. And several successful projects have come out of this area, including the Halide project, which you guys have heard about before, Apache TVM, Taco, and many, many more. There are many successful DSL compilers in this area. And so let's look at how compilers actually address these problems. So first, these compilers all have they sort of separate the notion of what you want to compute, your computation, with how you're going to compute it. So your computation is usually described abstractly through some domain-specific language. And then you describe to the compiler separately how you want to optimize your program through a schedule. And this schedule commonly contains things like loop transformations, such as parallelization, vectorization, etc. And the big guarantee that these compilers give you is that as you apply scheduling transformations, you're guaranteed your code stays correct. And that's a huge win because you can apply whatever transformations you want at a high level, and you know that your code is going to be correct, and you don't have to worry about that as you do your optimization. Next, because you write your code in this domain-specific language, the compiler has a global view of everything you want to do. And because of that, it can perform a variety of global optimizations kind of across the stages of your computation. And finally, because you have a compiler, right, you can just kind of write a separate schedule for each backend that you have. And as long as your compiler supports that target architecture, you're guaranteed that you're going to end up with the correct version of your code on that system, and you can try out the different scheduling techniques to get best performance on that system. So compilers have been very successful in this area. But the kind of deficiency that is out there is that, what about distributed systems? Not many of these compilers are going to perform, are going to even support generating code for distributed systems. And here, I mean, a distributed system could be all the way something from like a giant supercomputer, even all the way down to just a small motherboard that's got several GPUs attached. And a common linking concept between these is that they all have distributed memory. You have to move memory explicitly between these processors in order to actually to operate on them. There isn't really a unified memory, or if there is, it's not as fast as kind of managing memory to actually put it locally near each processor. Okay. So while we don't have too many solutions for this, we have a big problem because distributed systems are going to exacerbate all of these problems from before. And notably, first, if you have a distributed system, you actually need to start communicating across your address spaces. And so in order to achieve the highest performance, for example, you need to perform a variety of optimizations here, such as overlapping the amount of the communication you do with the computation you need to do. Because if you're not doing anything while you're communicating, you're wasting flops on your machine. And this could be from communicating across the network to just sending data over the PCIe to your GPU. For another example here, why performance isn't composed. Well, a lot of times different distributed libraries expect data in a certain format, such as a row-based partition of a matrix or something. And if you need to go to another library that uses a column-based partition, well, you're kind of out of luck. Either you need to write this thing by hand or eat the cost of doing a transpose on your data. And so the cost of data reorganization in a distributed system is even more than on a single node. Then finally, modern machines that we have are pretty heterogeneous. They've got different numbers of processors, different kinds of processors, different network characteristics. And so like a one size fits all with a library is probably not going to give you the best performance that you can on every single machine. And so our work aims to address these problems. And the kind of key question that we're answering is, what are the right abstractions to compile tensor programs to run on distributed machines? And the answer, I think, comes with several caveats that we should keep in mind. The first is that this should be simpler for end users than whatever they have to deal with right now. Naturally, we want to make people's lives easier. Then second, we should be able to capture algorithms that already exist. If we already know for a particular tensor computation, what's the best way to write code for this? Well, we shouldn't make people eat a loss by switching to our system. But at the same time, the abstractions that we provide, we should be able to generalize them to all tensor programs so that we can optimize things, that are out there in the wild or codes that we haven't even written yet, but that we might need in the future. Okay. And so, to answer these questions, we introduced DISTAL, which is the Distributed Tensor Algebra Compiler. And what DISTAL does is it's a compiler for dense tensor algebra, and it's going to decouple things that are commonly intertwined when writing distributed programs. So in particular, we're going to decouple the actual computation you want to perform, the optimizations you want to do on it, as well as how your data is distributed along in your distributed machine. Okay. So here's a sort of overview of DISTAL and some example code you may write using DISTAL. So I'm going to go through the parts of it here to talk about it. So the first thing you're going to do as a DISTAL programmer is you're going to tell DISTAL how you want to organize your machine. In this particular case, we're going to say I want my machine to be organized as a two-dimensional grid. So this is a standard thing you want to do. Next, you're going to provide to DISTAL what computation you want to do, and this is going to be provided in a domain-specific language that represents an einsum notation style. So this is an einsum notation of matrix multiplication that we provided to DISTAL here. Next, we're going to tell DISTAL how do we want our data to be distributed. And so here so I'm going to talk about this, of course, later, but as part of a tensor's format, we're going to tell DISTAL, here's how I want my data distributed. And in particular here, I'm saying I want my matrices can be partitioned in tiles across my machine. Then finally, we're going to tell DISTAL through a scheduling language, a halide-like language, that how you want to actually schedule your computation onto the machine. And so here, there's several commands here. If you programmed in halide before, they'll look familiar. You've got some standard loop transformations, some reordering. Then we've got some new commands that actually are going to help us map a computation onto a distributed machine. And so this little code snippet actually implements the SUMMA algorithm on a cluster of GPUs, if you know that algorithm. So that's kind of the high level idea of what DISTAL does. And so now I'm going to go through individual parts of it to talk about what abstractions DISTAL provides for writing distributed code. Okay. So the first thing that we did was model our machines. So we're going to look at what DISTAL provides here. And so DISTAL is we're going to have the simple approach of saying, we're going to allow you to view machines as hyperrectangular grids of processors, where each processor is going to have a local memory, and it's going to be able to talk to all of their processors. And so, this is a pretty standard approach. So, we're going to take this approach as well, because one, we're now able to kind of talk about locality in the physical machine, that may or may not be there. Say this processor is next to another one, this processor is in the same row or column as another processor. And then also it's going to be nice to structure our machine kind of like the computations themselves. Tensors are multi-dimensional grids, and the iteration through them also has a grid-like structure. So mapping these things onto another grid is is intuitive and symmetric. And finally, you need a grid-like layout to express many algorithms on tensors anyway, so this is sort of a natural fit. All right. So that's all I want to talk about for modeling machines. And so the first big thing is talking about how do we talk about how our data is distributed, okay? And so this is going to be done through a domain-specific sublanguage called tensor distribution notation. And so the idea of this language is to basically say, for each dimension of my tensor, I want you to tell me how it's mapped onto a machine M. So here's a statement in tensor distribution notation. So I've got my tensor on one side, and in this case, it's going to be a matrix. It's going to be two-dimensional. And I've got my machine on the other side named M. And this sort of mapping operator is gonna tell us how the tensor is distributed, okay? So the idea here is that I'm gonna name each dimension of T and M. So here I've named the first dimension of Tx and the second dimension of Ty. And then I've named the first dimension of Mx as well. So dimensions of T that share the same name with the dimension of M are gonna be partitioned by that dimension of M. I was trying to write here, but it's not. Okay, whatever. So here, the first dimension of T shares the same name as the first dimension of M. So this first dimension of T is going to be partitioned by the first dimension of M. So I think the best way to understand this is to look at several examples here. So the first example is we've got a vector, and we're going to put it on a vector of processors. And so the natural thing to do as well, we can say we want to make a block partition of our vector. So what we can do is we can just give the first dimension of T the same name as the first dimension of M, and this is going to result in a blocked partition of my tensor onto my machine. And so note, this doesn't have to be if T doesn't necessarily have to have 4 elements here. If T had like 100 elements, this distribution would say the first 25 of them are going to go to the first processor in M, second 25 to the second processor in M, and so on. Okay. So now the example we just talked about, if we have this row-based partition of a matrix onto a vector of processors, we do this by partitioning the first dimension of T by the first dimension of M, and letting the second dimension of Ty extend in its full extent within each partition. And note, if I wanted to change this to a column-based partition of my matrix, all I would have to do is change this X, the mapping of X onto M here, and I change that to a Y. And that would result in a column-based partition. So it's sort of very concise in this notation how to describe different data distributions. So to give some more examples, this extends to higher dimensional machines. We can map a matrix by tiles onto a machine, onto a two-dimensional machine by naming the first 2 dimensions of T, X, and Y, then naming the second 2 dimensions of M, X, and Y as well. We can extend this to higher dimensional tensors we can map a 3 tensor in tubes onto a 2-dimensional machine. So by partitioning the first 2 dimensions of our tensor by the first 2 dimensions of our machine, and then letting the Z dimension of our tensor extend in each partition. So then this also extends to when the machine has a higher dimension than the tensor, and we can do some interesting things here. In particular, one thing we could do is we can use the star operator to broadcast a partition across a dimension of our machine. And so here, if I have a tensor and I partition it into tiles, then I can use the star operator in the 3rd dimension of my machine to replicate this partition across the Z-axis of the machine. And you can imagine this could be useful if I have a computation where kind of each slice of my machine is going to access the same piece of the tensor. Okay. And as a dual of this, I can also actually put an index value there to restrict a partition to live at a certain subset of the machine. And so here I've taken my tile partition. I'm saying it's actually going to live on z equals 0 of my machine. And this may seem like a bit of a weird data distribution, but some algorithms actually need their data to be mapped in this way in order to achieve a asymptotic bound on the amount of communication they do. All right. So I've described here how data is distributed in DISTAL through tensor distribution notation. And I want to emphasize that this may feel a bit disjoint from how we're going to talk about how computation is distributed. And I'm going to say that this is intentional, because in DISTAL, you can talk about these things separately. This allows you to perhaps optimize your data distribution for your computation. Or if you already know your data is distributed in some way, you can change your computation to then fit the way that that data is distributed. But these things aren't intertwined. All right. So they may feel a bit disjoint.
Rohan, there's a question in the chat from Bodo Schultz. Can you have overlapping partitioning, in quotes, to do Halo-like stuff?
So not right now. We're not going to directly support like Halo regions or ghost regions, like stencil kind of computations. However, it is possible to sort of express stencil like computations as sort of a higher order higher order tensor contraction. But we're not going to directly support stencils right now.
Yeah. Okay. Thank you.
There's a second question, Rohan, from Dimitrios. How come the computation distribution does not automatically follow the data distribution?
Well, because some you may want to do more complicated things on your computation than just how your data is distributed. I think we'll probably see some examples later, but your initial data distribution does not necessarily imply a way to distribute your computation, especially if perhaps like for an element-wise computation, perhaps your data distribution does imply a computation pattern. But for computations where you may have a contraction over an extra dimension or something, then you have sort of options about how you want to actually communicate that data, which doesn't fall out of the data distribution. If that's a satisfying answer. We'll see some examples of this later in the talk. Okay. All right. So now I'm going to talk about computation distribution in DISTAL. And so to do this, we're going to need to cover a couple preliminaries first. So the first is a notion of an iteration space. So an iteration space defines the actual computation we need to perform on our set of tensors. And an iteration space is a hyperrectangular grid of points where each point is going to represent an iteration within a set of nested loops. Right. So for example, here, if I've got this tensor computation for all I, I've got two vectors A and B. So for all I want A sub I to be equal to the sum of all B. So this corresponds to the set of nested for loops below. Well, this is going to have a nice rectangular iteration space, kind of where each point is labeled with an I and a J value. And so if I and J also range between 0, 1, and 2, then this is going to be a nice square iteration space where you have all the points 0, 0, 0, 1, all the way up to 2, 2. Okay. So this iteration space describes what computation we actually want to perform. So now to actually talk about how this computation gets executed, we introduce this notion of an execution space. And it's going to be basically the space of all processors in our machine cross a time dimension. And the intuition is that we can talk about how a particular iteration space gets executed by kind of mapping the iteration space onto our execution space. So intuitively, if we tell for each point in our iteration space kind of what processor executed this point and when in time that point was executed, we've kind of talked about exactly how our iteration space gets executed. So for example, if I had that iteration space from before where my points were all 0, 0 up to 2, 2, a kind of default mapping of this iteration space onto an execution space is as follows, where I map all of the points onto one processor, and then I linearize the points in time along that processor here. So I've linearized the points with the I dimension and then the J dimension. So my points are labeled I comma J. You see here, we're first doing 0, 0, 0, 1, 0, 2, and then 1, 0, 1, 1, and so on. This corresponds to standard like sequential or naive execution of my tensor computation. Okay. So the way we're going to optimize our execution of our programs is through scheduling. And so these scheduling transformations are going to change how we map our iteration space onto the execution space. And so note that some other common loop transformations are going to actually change the iteration space itself, like splitting or dividing a loop or reordering some loops. But the scheduling commands that I'm going to talk about today are just going to change how we actually map the iteration space onto the execution space. Okay. So now I'm going to talk about the three main scheduling commands that DISTAL supports for computation distribution. Okay. So first one is distribute. We're a distributed compiler. We better support some way of distributing your programs. So the distribute command is pretty straightforward. That you're going to be able to distribute a particular variable. So here I've got index variables I and j. So if I want to distribute the I loop, well, what I'm going to do is I'm going to place all iterations of I on a different processor at the same time. Okay, and so this corresponds exactly to what is meant by parallelizing your computation. Every processor is now going to execute a corresponding I iteration, and then they're going to do all the j iterations locally. All right, this is standard parallelizing transform. And so that's not too hard, but maybe some alarm bells should be ringing, because you're saying, what about the communication that's happening here? We just distributed a computation. What do we do about communication? So let's assume that our data is distributed in the following manner. So A and B are going to be mapped in a block partition onto our machine. So I've kind of drawn that out here. And so to think about how communication is going to work, we're going to use a notion called completing a program. So we could basically imagine that we run our program, and then for everywhere we actually needed to do some communication, we'll like insert a marker that we needed to do communication here. So right at each iteration space point I comma j, we need A of I and we need B of j, right? So this communication is going to have something like this. So for each iteration space point, we already have the value of A locally, so we don't need to do any communication for that. But at j equals 0, at every value of j, we need to go get a corresponding value from B. So at j equals 0, every processor needs to go get B sub 0. And processor 0, that data element is already local, but processors 1 and 2, they need to go get it. And then same for j equal 1, well, processors 0 and 2 need to go get that value. And then for processor 2, processors 0 and 1 need to go get that value. Okay. So if we do our communication sort of like this is clearly going to be correct, but this is probably not going to be the most optimal thing that we could do. It's not efficient to send a single message with one data element for every point in our iteration space. So the second command that DISTAL supports is called communicate. And basically what this allows us to do is this allows us to control how much communication we're going to aggregate into a single message at a time. And so what communicate does is it says I can schedule all of the communication for a particular tensor to occur at a certain index variable. So here, if I say communicate B at I, what I'm going to do is at the beginning of each iteration of I can look at all of the iteration space points underneath me. So at each iteration of I, each processor is going to look at all the j iteration space points underneath them and aggregate all of that communication into a single message. So the beginning of each I loop here, well, we're going to aggregate all of the requests for B into a single message. So the beginning of each I loop, we're going to go get all of the data of B and then proceed locally with no communication after that. And so here it's like if I had enough memory, then it would be reasonable to replicate B across all processors so we don't have to communicate at all during iteration of the program. But if I don't have enough memory, I actually want to stick with the first one where I only communicate one data element at a time. So communicate sort of encapsulates the memory versus communication trade-off in distributed programs, where the more often you communicate, kind of the less memory you need to use, but you're going to send more messages at that cost. And so depending on your particular machine and memory you have, you may need to control this thing. And so communicate has a nice interaction with like other transformations like tile loops. You can imagine you communicate in the granularity of tiles, or you can communicate entire tensors or replicate these things, right? And I want to note that this is sort of all you need to specify in DISTAL for communication. You don't need to worry about things about who is sending data to where, how is it getting there. This is all you need to say, right? So the final command is called rotate. And so rotate, I call a distributed symmetry breaking operation. And so to understand why that is, let's first figure out where is the symmetry that we're looking for, that is actually in our program. And so if we have our communication pattern from before we replicated B, if we actually look at what data is getting sent where during execution, this would look something like this. So at j equals 0, the 0th processor is sending this out to the other two processors. At j equal 1, processor 1 is sending B sub 1 out to the other processors, and so on and so forth. And so if I had many more processors here, this would be a broadcast operation where one processor is broadcasting their data to all other processors. Okay. And so depending on my architecture, maybe this is not the most efficient thing. Maybe we would want to do a systolic communication pattern or something instead. And the core problem that stops us from doing that right now is that the fact that we parallelize the I loop, but now every processor is starting the J loop at J equals 0. So every processor starting at J equals 0, so they're going to need the same data at the same time. There's some contention here that one processor has to send this out to everybody else. And so the idea with rotate is that what if we change the way we map our iteration space points onto the machine? We change the order in which they occur. So for example here, I'm going to rotate J by I. And what this is going to do is it's going to say, I want each iteration of J to start at the current value of I. So the way that this looks is as follows. So ignore the communication for now. Let's look at just the order in which we execute iteration space points. At P0, we have I equals 0. And so the iteration of J continues as normal. We go 0, 1, and 2. But now at processor 1, well, we have I equal 1, so we're going to start at J equal 1, then 2, then 0. And at processor 2, we're going to just start at 2, then 0, then 1. And the result of this rotation is now, if we look at the actual communication that's going to happen, at J equals 0, every processor actually has the data that they need already. And now, as we go to the next iterations of J, well, every processor is sort of lagging one behind in the J iteration to the processor to their right. So what's going to happen is that every processor can just sort of shift data to their left at each iteration in order to satisfy the request that each iteration space point needs. And as a result, a systolic communication pattern is going to emerge from this small loop transformation to the program. And this is pretty cool because usually transformations like this are sort of expressed through like an MPI shift. It's not a loop transformation. It's some like really gnarly change to your code. And we can actually extend the rotate command we can use the rotate command to express a variety of distributed algorithms that use systolic communication patterns. Okay. And to give a little bit of intuition for how rotate works, well, we're going to use the modulus operator in the generated code. And so you can imagine if we have a loop that loops over the J variable here, what I'm going to do is I'm going to transform this into a new loop that iterates over a fresh variable J prime over the same extent. And then I'm going to recover J by kind of offsetting J by I. And then I'll use the modulus of the original extent in order to make sure that this offset wraps back around, that I touch all the same points I would in the iteration space normally. Okay. So that was the final scheduling command here. So we had distribute, we had communicate, and we had rotate. So the natural question is from before, like, okay, how expressive are these abstractions now that we have them all in our hands? And it turns out that they're extremely expressive together. So what I have here is I've written out several well-studied matrix multiplication algorithms dating back to the first distributed matrix multiplication algorithm, Cannon's algorithm in 1969, all the way down to COSMA, which was proposed last year in 2019. And it turns out that all these algorithms have very different pseudocodes, very different communication patterns, such as Cannon's algorithm at the top, it has a systolic communication pattern, down to some other more exotic communication patterns where you have a three-dimensional grid and you're sort of shifting data along this grid, like the 2.5D algorithm from Solomonic. But it turns out that if you look at these things all in the lens of DISTAL, they're actually not very different. They just have different initial machine configurations, different initial data distributions, and then slightly different schedules. So when you look at the kind of core components if you look at this as terms of what DISTAL can do, all these different algorithms are just expressible as different inputs to the DISTAL compiler. And to sort of give you an intuition for how this works, I'm gonna rederive the SUMMA algorithm in DISTAL. And so this algorithm is a well-known matrix multiplication algorithm, and it is actually used in the Scalapack library. Okay. So to understand,
Rohan, before you go there, there's another question in the chat.
Yes, go ahead.
How do you know that this rotate stuff doesn't change the semantics?
So we know it doesn't change the semantics kind of. So I guess I didn't define explicitly in this talk, but so the operations that we're allowed to perform in tensor algebra are basically multiplications and additions, both of which are commutative. So so we can do this rotation for commutative operators. Note if we extended the language to support non-commutative operators, we would have to restrict rotation to just things that we can prove or user annotated as commutative. Okay. Okay.
Yeah. I mean, their addition is only commutative on floats up to approximation anyway. So
yeah,
you're not worrying about those approximations.
Yeah, I mean, a lot of times distributed computations are reordering the computation anyway to some point to achieve some sort of parallelization. So you're probably not going to get a floating point equivalent result as like on a single node. But yeah, mathematically we're commutative.
Yeah. Okay, thank you.
So it's coming to the SUMMA algorithm. So to describe this, I'm just reminding everybody what the actual Einstein notation for matrix multiply is up at the top. And so the way that this algorithm works is that it's going to organize our machine into a 2D grid of processors. And then we're going to tile our matrices A, B, and C onto each processor as well. So now each processor is going to operate on a local tile of A. And what's going to happen is now in parallel, each processor is going to iterate through the entire K loop of this computation, the actual contraction loop. And so this is an outer product algorithm. So intuitively on a single node, what this would look like is that you're taking vectors of the matrices at a time and you're doing an outer product between them to kind of fill in the values for the entire matrix. You're taking the outer product and then accumulating that value into the rest of the matrix at a time. So here we're going to iterate through the K loop in chunks, and kind of each process, as we have a chunk of rows from B and a chunk of columns from C, the processors that own each piece of this chunk as I've drawn up here are going to broadcast this data down to their columns and across their rows. And so after this communication, then everybody's going to take these chunks that they received from the communication and then do an outer product there locally and accumulate it into their matrix. Okay. So every processor is we're going to sort of step across the matrix in chunks of vectors like this, and every processor is going to accumulate their local piece into a local tile of A. Okay, so that's the SUMMA algorithm at a high level. And so let's see how we would write this in DISTAL. Well, we first have to organize our machine as a 2D grid. It's not too hard. And then we already talked about how to organize matrices into tiles. So that's also not too hard. So now let's actually schedule our computation. So here's an example of how the initial data distribution doesn't really give you a scheme for how to do your computation. So here I'm gonna talk about this. To sort of express the transformations that we're gonna do, I have this naive matrix multiplication pseudocode, and we're gonna see how the scheduling transformations are gonna modify this code. All right. So the first thing I'm gonna do is I'm gonna tile my I and j loops of the computation. So I'm gonna do this with the divide command. So divide is a loop splitting operation where the outer loop has a constant extent and the inner loop has a variable length extent. So I'm going to tile my computation over I and j. So I've got tiles of I and j, just like SUMMA was doing before. And next, I'm going to split the K loop so that now we have a variable size outer loop and a constant size inner loop. So K has been split into chunks, just like the SUMMA algorithm already. That one was iterating through chunks. And so if you look here, now we've got a loop for each tile, then a loop over the value over chunks of K. And then inside that, I've got a local matrix multiplication. And so this is getting pretty close. So now all we have to do is we have to map this onto our machine. So we're going to do this by distributing the I and j loops, IN and JN loops. So now we've got a distributed operation over all the tiles of our computation. And so now we need to just figure out how to do communication. So first we note that we've got a loop over all the tiles. So every tile is now running the K loop in parallel, which is what we want. So now we're going to communicate A underneath JN. So this is going to say that every processor is going to get a tile. Every processor in our grid is going to get a tile of A to work on. And now we note that SUMMA was iterating through B and C in chunks, and the owner of each chunk was sort of sending this data out to the other processors. So if I communicate B and C underneath K0, I'm gonna communicate B and C in chunks, exactly like SUMMA. And we can do analysis to then figure out exactly the corresponding pieces of B and C that need to get sent to each processor here. And assuming you can do that, this code actually implements the SUMMA algorithm, and we've sort of derived it from loop transformation, derived it from the original matrix multiplication code, rather than sort of writing a separate MPI implementation that has all sorts of details we don't need. Okay, so this is an intuition for how you can describe all the other algorithms. It sort of follows a similar procedure, but this is to give you a taste of how that's implemented. Okay. So I've talked a bunch about the abstractions DISTAL provides and what we can do with them. So now let's pull back the covers a little bit and talk about how DISTAL is implemented. So a little bit of that. So the first thing that we're going to do in DISTAL is we're going to take our Einstein notation kind of DSL, where the loop iteration ordering is unspecified, and we're going to do a straightforward transformation to lower it into an IR called concrete index notation, where basically here we just are going to start to specify the actual loop ordering we have. So here before the IJK loops in this computation are not specified, but now we're going to say, okay, if we have actual IR where we say the first thing we're going to do the I loop, then the J loop, and then the K loop. And the point of this is now that our scheduling operations are going to rewrite this IR to kind of just to talk about the transformations that we're doing. So for example, if I have a particular for all statement where I have a for all I, and I want to divide this I into two in an outer and inner loop, well, I can do a rewrite that actually splits that loop into two pieces, IO and II. And then I'm going to write on the side of my IR that, hey, this is how these two variables are related. The I0 and II variables, they were the result of dividing I into pieces. Okay. So the scheduling transformations that we have are going to be expressed through similar rewrite rules like this. So if we want to distribute a particular variable, well, we don't need to change the loop. We just need to mark down on the side that we wanted to distribute such a loop. If we want to rotate a particular variable t by a set of variables I, well, we just need to swap out, similar to the transformation from before, we swap out the variable t with the result of the rotation r, and then write on the side that we did the rotation. Then finally, if we want to communicate a tensor to a particular variable I, well, we need to just write down that we did that. And so these transformations don't do that much right now, but we sort of need this information laying around so that whatever backend we compile to has enough information to then kind of implement these commands faithfully. You know, depending on the backend, we might need to do more analysis to implement one of these things. Okay. So before I talk about the backend, I want to talk a little bit about how we compile the tensor distribution notation sublanguage. And so the intuition here is we can compile this into a concrete index notation statement that if you ran it would put the data exactly where you need it. Okay. So for this row-based partition that I had before, we've got the variables x and y, and then we've also named the first dimension of mx. So first thing I'm going to do is I'm going to compile this I can translate in a statement like this, where I have a loop over the entire tensor. So I've got variables for x and y, and I'm like sort of naming each element in my tensor. And now, well, I said that the first dimension of t was partitioned by the first dimension of x. So I can express that by, well, I divide x into a loop for each processor in M, and then an inner loop for like the actual elements for each processor. And then now I can give like those corresponding chunks to each processor by applying the distribute scheduling command and then communicating t underneath that distributed variable xo. And this kind of transformation is going to give us a piece of code where every processor is going to iterate over a chunk of rows corresponding exactly to the way that we kind of intuitively described with the tensor distribution notation. Okay, so that's the high level of how this gets lowered. So what is the backend? What's the final step in this compilation process? Well, we're going to target the Legion runtime system. So Legion is a distributed task-based runtime system. And there's basically this notion of tasks in Legion where tasks are going to operate on bulk data. And the runtime system is going to move data between processors for your tasks to actually operate on. And so the runtime system will perform a dynamic analysis based on what tasks say they need, it's going to move that between the processors. Okay. So naturally, the three commands that we have are going to be mapped onto Legion by saying, okay, if I want to distribute a particular set of variables, well, I need to launch a set of parallel tasks here and tell Legion to parallelize these across the machine. If I want to communicate a tensor in a particular loop, well, I need to tell Legion, here's the data I want you to transfer and how I want you to transfer it around. Then finally, rotate is going to be implemented with this loop transformation with modulus. And so then there's going to be some like interactions between communicate and rotate in order to get the systolic patterns to work out. Okay. So kind of, I've talked a bunch about DISTAL now. So now the question is, how well does all of this work? So there's two main comparisons that we're going to do here. And the first one is going to be for distributed matrix multiplication operations. And the goal of this comparison is to evaluate our performance on a highly optimized kernel. And so here we're going to compare against COSMA, which is probably the best known matrix multiplication implementation out there right now. The Cyclops tensor framework, which implements the 2.5D communication avoiding algorithm, and the well-known library Scalapack. Okay. And then next, we're going to talk about higher order tensor kernels. So these are kernels that perhaps haven't got much attention from researchers, but still exist out there. And they sort of represent the long tail of tensor computations we may need to optimize. And here we're going to compare against Cyclops tensor framework, which is the only other system we know of that supports kind of general distributed implementations of any tensor kernel. So before I get into the results, just some like bookkeeping details. So all of these experiments were run on up to 256 nodes of the Lassen supercomputer. So each node on Lassen has 4 V100s and 40 power 9 CPUs. So all of our systems are going to be configured to use the same BLAS and cuBLAS for GEMM. And so all experiments will be weak scaling. So if you're not familiar with weak scaling, this means that the memory per node memory used per node for a problem is going to stay the same as we increase to two nodes. So for example, if we have a problem size P on 2 nodes, as we go up to 4 nodes, we're going to double the problem size so that the actual problem size per node stays the same. And the reasoning for this scaling is sort of, you can imagine that if I achieve some % of utilization at some node count, if I increase to more nodes, but also increase the problem with the same factor, I should stay at that same utilization as I go up to more nodes. And this is a common evaluation metric in high performance computing applications. And so we're going to report all the results in GFLOPS for compute-bound applications and gigabytes per second for bandwidth-bound applications. Okay. So the first set of results we're going to look at is the GEMM computation on CPUs. And so I'm going to highlight certain parts of results at a time. So here, we're going to first look at the baselines that we're comparing against for CPUs. So we've got COSMA up at the top. COSMA achieves near peak utilization and has perfect weak scaling performance. Flat lines are great for weak scaling, and we want these to be high as possible. And a bit lower than that, we're going to see that CTF and Scalapack have reasonable weak scaling behavior, but they just don't perform as well as COSMA. Okay. And then the code from DISTAL. So what we've done to evaluate this for DISTAL is we've taken all those matrix multiply algorithms I showed you earlier and implemented them all as schedules in DISTAL. And so as you can see, most of the algorithms perform pretty well. There's some deviation with some of the algorithms. They don't perform well at these particular core counts. And as we can see, there isn't that much of a variation between the algorithms themselves. And that's because on CPUs, the GEMM computation is so compute bound that you can hide all your network latency by just doing computation while you're communicating. And so there isn't that much variation between these algorithms, on CPUs at least. And the kind of takeaway here is that, well, our best performing schedule comes within 95% of Cosmos performance, which is pretty crazy for a system that is not matrix multiplication specific at all. And this slight performance gap comes from the fact that Legion uses a couple of cores at runtime in order to do some work and do some analysis. And the cost of that seems to be very little. We can achieve pretty close to peak performance. And the benefit of all this is that the compiler is much simpler engineered because it can leverage the runtime system when it can. Okay. So now I'm going to talk about GPUs. So here for multi-GPU distributed matrix multiplication, we compare just against COSMA because COSMA is only one of these systems that had a multi-GPU implementation. And so COSMA here achieves kind of half of the peak throughput, and it has pretty good weak scaling out to 256 nodes. And so the way COSMA works here is that COSMA is going to keep all of its data in the large CPU memory and kind of ship tiles of it over to each GPU in order to do the per node matrix multiplications. So in comparison, so now we actually see a bit of a difference between our matrix multiplication algorithms, and I've grouped these results in kind of two families. So the first family is a group of matrix multiplication algorithms known as 2D algorithms. So these algorithms, as it kind of sounds, they organize the machine into a two-dimensional grid, and so they trade off using less memory per node for more communication. And so these algorithms, because of that, they're gonna so they perform pretty well on square grids, but as soon as you get to a non-square grid, they don't perform as well. And they see the same variation we saw earlier with CTF and Scalapack. And the kind of reason for this is that for the really large matrices you need in order to actually saturate the 4 GPUs on a machine, you need some pretty giant matrices. And that results in you sending like gigabytes over the network to actually do your communication. And so this makes the algorithm actually pretty sensitive to the communication you have to do, and it's sort of evenly balanced between communication and compute. So therefore, we see like sensitivities of the network are actually going to result in huge changes in performance. Okay. And so the next family of algorithms is called 3D algorithms. And so as it sounds, these algorithms organize the computation as a 3D grid, and they're going to trade off using more memory per node. They're going to replicate data at the benefit of not communicating as much. So we can actually see this effect in two of the algorithms, our implementation of Johnson's algorithm and our implementation of COSMA, is that they actually don't scale beyond 16 nodes because they replicate data. And so that the GPU runs out of memory to actually hold as much data as needed to run these algorithms. And then the final algorithm is the 2.5D algorithm from Solomonic. And this algorithm, as it sounds, kind of interpolates between the 2D and 3D families where and you can see it sort of gets better performance on these non-square grids and achieves similar performance on the square grids. And so the takeaway here is that we can also achieve a pretty competitive GPU performance for matrix multiply as well compared to a hand-engineered system. And so we think these results could also be made better through just making better use of generating better code on our end. So now I want to talk about higher order tensor computations. And so here we compare against Cyclops Tensor Framework, as I said. And so to give an idea of how Cyclops Tensor Framework works is that it's built around this fast distributed matrix multiplication implementation. And so for any tensor computation, it's going to look at that computation and be like, how can I convert this into a series of matrix multiplications? Okay. And so it achieves distributed implementations of a tensor kernel by just casting the computation down into a set of distributed matrix multiplies. And so while this is going to be correct, it's not going to be the most efficient thing you can do. So here I've got the tensor times vector kernel here, which is kind of an element-wise operation. And Cyclops Tensor Framework is going to perform pretty poorly on this because it's going to try and cast this computation into a series of multiplications against this vector C. And that's going to be pretty inefficient. This would be not really make good use of the machine when you could do sort of an element-wise operation that has no communication. Another kernel we looked at was the tensor times matrix kernel. And this kernel is, you can look at it as a series of I-independent matrix multiplies. And so with DISTAL, we can write a schedule that is going to, in parallel, do all these parallel matrix multiplications with no communication. But Cyclops Tensor Framework is going to do a series of distributed matrix multiplications, which is going to result in a big performance hit as soon as you move off of one node. Another computation we looked at is the inner product kernel, and this is just sort of a global reduction. And my point here is that CTF actually does pretty well on this kernel, and that's because a general library can identify several useful kernels and implement optimized versions of those. But there's only so many kernels you can actually do this for. Eventually, you're going to hit some kernels that your performance just sort of falls off a cliff. And so with the compilation-based approach like DISTAL, you can get the best kernel every time. And then finally, the last kernel we looked at was the matrix-sized tensor times Cauchy-Rao product kernel. And the interesting thing about this kernel is that there was recent research that published a distributed algorithm for this kernel. And with DISTAL, we can just implement that in 10 lines of scheduling. And we can get a computation, an algorithm that we know is going to perform well because it has proven guarantees rather than like an interpreted version of the kernel. So now I'm going to just throw up some results that we had on GPUs. So we couldn't get Cyclops Tensor Framework's GPU backend to work here. So we just are comparing against our CPU implementation of each kernel. And the kind of point I want to make here is that with a code generator, you can easily target different backends. And you can get huge benefits, especially you can get large benefits in bandwidth. And then especially for compute on tensor computations on GPUs, you're going to get gigantic improvements. So supporting GPUs is a big win for compilers, and we can get great performance there as well. So this is going to sort of wrap up my talk, and I want to leave with a couple conclusions about the work that we've done. So first is that DISTAL is going to combine these separate specifications of data and computation distribution, kind of things that are commonly intertwined when writing distributed programs. And using these separate specifications, DISTAL can represent many existing algorithms and can allow you to optimize computations that don't even have algorithms out there for them. And finally, DISTAL can be implemented to achieve high performance on modern machines. Kind of equaling the performance of hand-tuned libraries are coming close, and then beating general purpose libraries by allowing you to generate specialized implementations. And so in the future, we're looking at extending this work to sparse tensors. And the vision I have is that you can imagine we could have a distributed implementation of any tensor program out there, along with any format the data is in. You can have your data in any format, and you can scale this data up without converting it into different format to a cluster of any size. And that's sort of the vision that I have, and that's what we're working towards. So that's going to conclude my talk, and I'm happy to take any questions now.